Okay, announcements. Homework is due now. The last problem set of the semester, and if you're not taking 214 of your life, is due today. Review session tomorrow, 5 o'clock in Turnerson, or whatever I said on my email. It was originally scheduled for 4. Because I'm interviewing with MSMS to be their new teacher, I may be a little bit late. If I am late, I will tweet it out so that people know that I'm at least coming. That said, that's on Thursday. Let's go do this. This is the November 2016 test 3 of 213. We're going to do the multiple choice first, and then we'll do the problems, and if we have time left, we'll address any further questions. Two strings are of identical length, material, and tension. Both resonate at the first harmonic. One is thick, one is thin. The thinner string has blank, higher frequency. Tension of a string has what units? Newtons. Hooke's law in vector form is what? E. Units of pressure are newtons per square meter. Now, for number 5, let's see if, oh yeah, here it is. Which string of the following is vibrating at its second overtone? Oop, let me include the whole thing, that'd help. Second overtone. It's 3 that's the second overtone, so it is D. The velocity of sound in a vibrating string is D. A string vibrates at its third overtone. How many antinodes are there? So a third overtone is what harmonic? Fourth. So if it's at its fourth harmonic, how many antinodes are there? 4. So really, the N is the number of antinodes there are for a string. What is the equation for frequency found, or frequency of sound heard by a moving source moving towards the observer? B. Spring pendulum has a period of 2 seconds. This thing is not focusing as well as I want. Spring pendulum has a period of 2 seconds. You quadruple the mass. Its new period is what? It's 4. Spring pendulums are mass dependent. In fact, it's M over K. So if you quadruple the mass, you double the period. String 2 is vibrating at its second harmonic, or A. Which string has 3 antinodes? 3, or A. You measure the period of a simple pendulum. It's 3 seconds. Simple pendulum with 3-second period. You increase the mass at the pendulum. Its new period is 3 seconds. Simple pendulum are not mass dependent. Which string has only 2 nodes? 1, or C. What is the inverse of frequency? Period. The units provided by 1/2 rho v squared without any conversions is, it's A, newtons per squared meter. For a string, the first overtone is the same as second harmonic. Object is negatively buoyant. Which of the following is true? C. A spring pendulum is gravity independent. Which string is vibrating at its third overtone? Third overtone, which one? So third overtone will be string 4, yes. What is string 4's harmonic? So third overtone is what harmonic? 4th, yes. For a resonating half pipe, a pipe closed at one end, the third harmonic is same as the first overtone. 21, lambda, not wavelength, is what? Mass over length. When n equals 2 for a resonating half pipe, its frequency is called what? Cannot have that value, E. A moving observer away from the source has what as its frequency heard? D. It's going to be lower pitch. It's a moving observer, so that's in the numerator. What is the equation for frequency of sound heard by an observer moving towards the source? Well, if that's away, then that's towards. So E. Last, when n equals 3 for a vibrating string, it is vibrating at the third harmonic. All right. All right, now we'll do the problems. This is, forget what version it is. Probably, it's either number of oscillations, is my guess. So given the spring shown below, how long will it take to oscillate the specified number of times? So period is total time divided by the number of oscillations. Total time, number of oscillations by period. This means number of oscillations, 2 pi m over k. Oh yeah, I need to zoom it out. So that'll give you the total time. The one problem that we don't have, or that we do have, is one of the problems is we don't have mass. The other problem is we don't have K. However, we do know that it stretches from its rest position a distance of x, which is equal to 10 over pi squared. This spring force is related to Hooke's law, which is kx. When it's hanging in its rest stretching position, the sum of the forces is equal to 0. You have kx up, you have mg down, so kx minus mg, or mg equals kx, and k is equal to mg over x. So that's the spring constant as a function of m. Plug in m. N equals, or actually, time equals 2 pi n mx over mg. My m's cancel. M was not necessary. Probably during the test I frequently answered the question, am I doing it right, with it is a correctly constructed problem. So 2 pi 30, 10 over pi squared for x, g is 10. The 10s cancel, I'm left with 1 over pi squared, so 2 pi 30, square root of 1 over pi squared. Those cancel, and the total time is 60. You can tell that it was a desperate play to get the numbers to work out right, because the extended length was 10 over pi squared. That was kind of specific. Next, we have a bucket. The depth underneath the surface is 20 meters. There is a hole. The radius is 1 over pi square rooted. The volume above that line is 12,000 cubic meters. A cylinder with a hole is shown below. How long will it take for the specified volume to come out of the hole? Now, one of the things that was specified during the test is that the velocity of the water coming out of the bucket was constant. The level of the water remains the same height. This is a Bernoulli's equation problem. P1 plus rho GH1 plus 1/2 rho V1 squared equals P2 plus rho GH2 plus 1/2 rho V2 squared. Now, looking at the hole, they both have the same physical height with respect to the center of the earth. Here outside, there is a velocity 2 at a particular pressure 2, which is atmospheric pressure. Over here, the velocity is equal to 0. The water is coming in from all sides, so the net velocity of the water shooting out of that hole is a constant, or is actually, and is 0. The pressure is atmospheric pressure plus rho GH. H is the depth under which this thing is situated. So those would cancel since they're at the same height. That one goes away, and I'm left with this. P1, atmospheric pressure, plus rho GH. P2, atmospheric pressure, plus 1/2 rho V2 squared. Atmospherics cancel. I'm left with rho GH equals 1/2 rho V2 squared. The rho's cancel. Solving for V, 2GH V2 squared square root of 2GH is equal to V2. So 2 times 10 times 20. 20 times 20 is 400. Square root of 400 is 20. And so the velocity of the fluid coming out is 20 meters per second. To get the time, the flow is area times velocity. We use the equation of continuity. The volume is the flow times time, or area, velocity, time. So volume divided by area times velocity, and my velocity will be a little bit more scripted than the volume, is equal to T. The volume is 12,000. The area is pi r squared, and r is 1 over the square root of pi. Velocity is 20. 1 over square root of pi squared cancels with that, and I'm left with 12,000 divided by 20, 1,200 divided by 2, or 600 seconds. And so that's the answer for problem 1. Okay, problem 2, Atwood string. The links are not given. One of them is missing. It's not to scale. The frequency of the vibrating string is 2,000 hertz. The mass of the string is 10 grams. It's at its first overtone, so N is equal to 2. Determine that hanging length. So the frequency is NV over 2 times the vibrating length. Excuse me? I can't hear you.
The hanging length says 1,000.
No, the mass hanging is 1,000. I'm looking for the length itself.
Sorry.
The vibrating length is L1. Velocity is the square root of tension divided by linear mass density. Linear mass density is the mass of the string divided by the total length, which is L1 plus L2. Velocity, taking this into account, is and T is equal to mass hanging gravity. So the velocity of sound in this thing is mhg over ms L1 plus L2. I think that's all I need. So F is equal to N over 2L1 square root mhg L1 plus L2 ms. Solve for L2. First thing I got to do is square. F squared, N squared, 4L1 squared, mhg L1 plus L2 over ms. Separate, put everything over on the other side with the exception of the L1 plus L2. F squared ms 4L1 squared over N squared mhg L1 plus L2. Remove L1. F squared ms 4L1 squared over
n squared mhg minus L1 equals L2. And there we go. Plug in values. 2,000 squared. MS, 10 grams, 0.01. 4. L1, 0.2 squared. Divided by N2 squared. MH, 1,000. G, 10. And that gives me, and minus 0.2. And that gives me L2. That will cancel with that, so I'm not going to worry about it. So 2,000 squared times 0.01 times 0.2 squared divided by and I think, see if I did the math right. There may have been a mistake in here. Because I think what I ended up having to do is I had to change a number at the last minute. So the answer for this is coming out negative 0.04. Now what I did is, I made a mistake when I was doing the initial calculations. And so what I did is, I looked at it and went, I'm gonna make, like I called an audible and I said, well, instead of 10 grams for the string, I made it 100 grams. So plus 0.2 times 10 minus 0.2. And so I get 1.4 meters. So what it was is that I used too low of a number. So I just said the mass of the string is 0.1. Yes. That's the hanging mass. Oh, yes it was. So this is one of those situations where someone probably did it correctly and said, are you sure this thing is going to give me a positive number for L2? And I would go, okay. And actually, I think I remember, there were 3 versions of this. The other 2 worked out correct. And this is the 3rd one. This is the one with the wrong answer. So one of the versions had a bad number. So I had to fix it. But that setup is, there's nothing wrong. As an undergraduate, I was said, solve for L2, you need an equation. You know you're plugging. All right. The last problem you're in a car passing a siren. What is the velocity of the car? I did not give you specific frequencies. All I gave you was the ratio of frequencies. That the frequency towards is 1.5 times the frequency that you hear as you go away from it. This is a roulette wheel problem through and through. So frequency towards, it's a moving observer, is frequency times 1 plus V over Vs. The frequency away
is frequency 1 minus V over Vs. Those cancel, and that ratio is equal to 1.5. So to solve for V, cross multiply. Distribute. Bring that over there, that over there. Well, 1.5 minus 1. Factor it out. .70 meters per second. And so what I did was, this is kind of a little bit of a simplification of a standard roulette wheel problem. And so there you go. So that's the test. Or that was the test that we did a year ago. 27 minutes. How bad can it be? In the, what we're going to do, we're going to quickly go back to review number 1, or the bucket problem. So in Bernoulli's equation, that's Bernoulli's equation. When you've got water, the 2 points that we're using, one point is immediately inside the bucket, the other point is immediately outside the bucket. Outside the bucket, the water is obviously moving with the velocity v. Inside the bucket, the water, if this is the hole, the water is coming in from all sides. There's a little bit coming in from the back, but for a lot of it, the rationale is the velocity of the water just inside the hole is very small. So you can say that it's 0. The height, the physical heights are the same. So where you've got the Bernoulli's equation with the height going down the hill, the difference in the height is important. Because the points are exactly the same height, similar to the shower curtain problem, those things cancel. The difference comes from the pressure. The pressure outside is simple atmospheric pressure. The pressure inside is like gauge pressure. Total pressure is atmospheric plus the depth of fluid stacked on top. And so that's the setup. Yes?
So the people inside the atmosphere proportional.
Yes, because at that particular point, you're resting underneath a column of fluid of depth, what I call H, or it's a little bit more complex than H1 and H2. H1 and H2 are the physical heights. H is the depth below. And then on top of that is atmospheric pressure. So granted, a difference of whatever that difference was, 20 meters or something, there's a very itty bitty change in atmospheric pressure, but it's not enough as much as 20 meters.
So in the actual equation, it's the cross out rows, H1, rows, H2, and what we plug in the P1.
P1 becomes P atmospheric plus rho GH, where that new H is the depth underneath. Okay, for the appetizer? Yeah. So the atmosphere, or I'm sorry, for the appetizer, period is total time divided by number of oscillations. So the total time is number of oscillations times the period. You substitute in for the period. Now the problem with this is people who took this test said, you didn't give us the mass. And I said, I know. It's a correctly constructed problem. So if I don't give you the mass and it's a correctly constructed problem, you don't need it. That's inferred. Or conferred. I did give you the stretch distance, which curiously enough was 10 over pi squared. You know Hooke's law. You stretch a particular distance x, there's a force of kx. You've done the period lab. Period of a spring. What you do is you let the mass hang, and eventually it'll come out of your hand, and then you measure the change in distance. So kx is equal to mg. So you solve for k. K is a ratio, mg over x. Substitute that into your period equation. And what you notice is that the mass is canceled. So you don't need the mass. And then you just run it through. Then it's just solved. Yeah. 1 over k becomes x over mg. So you can see it. The substitution is done right there. Yes. Hold on. Oh, for the multiple choice? If you quadruple the mass, I know which one you're talking about. So that's the initial period equation. The new period is 2 pi m prime over k, where m prime is 4m. Plug that in. So now I get that. Well, now I've got a 4 inside the square root. I'm going to pull that out. Which gives me this, which is 2 times the initial period. So if you quadruple the mass, you double the period. If it's a simple pendulum, yeah, it remains the same. Yes?
So on the problem 3, you only wanted velocity because there's a question mark beside the frequency away.
Oh, I may have asked for something more. Hold on.
Like in the question, it says velocity, but then there's a question mark beside frequency away.
Oh. What frequency away and question mark in that particular case, I think it's a valid question to ask during the test.
Okay.
What that means is I didn't give it to you.
Okay.
So it's not a, I don't think you have enough information to find it.
I was just making sure.
Yeah, it's a good question. Well, she was asking about what does that mean? And what it means is, I think a lot of times what I really should put is unknown, because you interpret that as I'm asking for it. So it's a valid question to ask during a test. The clarification would be, that is a good question, I don't want that. It's purposefully not given. Yeah. Okay. Next question.
The source is moving towards an observer. Did I answer? It should be that.
We're going to clarify. If it is an observer, the frequency that you hear towards or away, the parentheses are in the numerator. If it's a source, the frequency is in the denominator. Now, observer, source, towards, away, moving observer is F1 V over Vs, F1 V over Vs, moving source F over 1 V over Vs, F over 1 V over Vs. For towards, it will always be a bigger number, so that has to be positive and that's negative. For moving away, you have to hear a lower frequency, so those are minus and plus. And so that's, if you want a moving observer away, you need this. If you want a moving source towards, you use this. Yes?
We go back to right after we talked about on the last one.
Hold on. What's your question?
It's on authorship and right after we talked
You're talking about the dollar shift that we did on the test.
Yes.
Okay.
So what was given to you was the ratio. Towards over away was 1.5. So what I did was, this was a moving observer. So I just plugged in the appropriate equations and set the ratio to be 1.5. Then the rest was just algebraic manipulation. That's why towards has plus. And
So when you took B over BS out, like you got them on the same side, you factored it out, there's still a one there.
yeah.
If you move the one, that's what I was confused, because you moved.
Yeah, I took that whole thing in the denominator and I moved it over to the numerator on the right side. Then distributed, got my B over BS terms on the same side, factor out, and so on.
You would not do this, and over there, it's still within like, within the same things that
You would have to have plugged in the frequency. I was trying to, a lot of times in an effort to make it simpler, everyone just freaks out and makes it way more complex. Follow last year. Question. We could, oh goodness, it's 3:12. We just run through that fast. We can hang out till 3:30 though. Yes. With the half pipe I'm doing what? No, for a resonating half pipe, the evens are eliminated. So 1, 3, 5, 7, 9, etc. are all allowed. 2, 4, 6, 8 are not. So if you have a half pipe, or if you have a pipe open at both ends, and it's resonating at the second harmonic, you shove a fork into one end of it, it cannot resonate at the second harmonic. It will now resonate only in first verse. Half pipe, fifth harmonic is what overtone? Second, exactly. First, fundamental. Third, first overtone. Fifth, second overtone. That's when it's those overtones. Third harmonic for a string is what overtone? Second. Fundamental, first overtone, second. I pluck a string. I increase its velocity of sound in the string. What happens to its frequency? It increases. If I increase its linear mass density, will the frequency increase or decrease? It will decrease. If I increase its harmonic for a string, will the frequency increase or decrease? It will increase. If I increase its harmonic, its period will what? If I increase the harmonic on a string, what will it do to its period? It will decrease. You increase the harmonic on a string, frequency goes up. Period is inverse of frequency, so it goes down. Let's try to trick you. I was successful. I increase the velocity of sound in air. A pipe's resonant frequencies do what? What's the frequency of a pipe? In what over what? NV over 2L. So increased velocity, increased frequency. I increase the length of the pipe, its resonant frequency does what? It decreases. So if it's in the numerator, it's directly proportional. Increase that factor, increase the result. If it's inversely proportional, it's 1 over that quantity. Increase that quantity, decrease the measured quantity. In physics lab, on the Mondays, we were measuring the speed of sound in air. Were you using full pipes, half pipes, or strings? Half pipes. Because what was the water doing? It was, it was blocking the in. Number of nodes in a first overtone. 3. A first overtone is what harmonic? Second overtone, or second harmonic. Second harmonic is the number of antinodes. Add 1, you get the number of nodes. I'm gonna keep, as long as I'm killing time. Let's see. 14. God, 14. Yes. Hold on. Oh, I factor out a V over VS from I factor a V over VS. V over VS times 1 is V over VS. 1.5 times V over VS. Oh, it would have just, I would have just flipped that equation. I would have written FA over FT, 1 minus V over VS over 1 plus V over VS is equal to V1.
So it
It would
just
just flip it. All right, any other questions? Now, once again, we're going to do, I can help 214 students all day long. We're at the end of our road. Do we need a review session tomorrow? Yes? Okay, all right, we're still. All right. You got to have a review session. Give me one last problem to work on, and then we can go. Yeah. Oh. Okay. That's not a problem. Who's got a problem in the middle? Someone has. Yes. Yes. Frequency one for sure? Yeah. Could be. I don't know about the fluid. I mean, fluids is kind of an open-ended problem. So, no problem. With one of the things that I try to do is, if there are hybrid problems, there are hybrid problems within the test material. In the final, I could do a torque bar with a buoyancy problem and put those two together. It's not. I will say that the only way that one part comes into play is with the pole and the mass on the end, you've got a string that you flex. That can be done. Though Atwood's machine, Atwood's string problem does that quite well without torque. So there's no real point in having it. Yeah, Atwood string is going to be on it, so I would want to design having mass on it. All right. On the floor, I have a moment. Yes. I mean, we've just gone over it right now. Yeah, we've discussed what this is. Probably the biggest wild card